fabric of reality beneath you is stretching and compressing in ways that would have seemed like pure magic just a century ago. The space between your body and this screen isn't the empty void you think it is. It's a dynamic, flexible medium that can be twisted, warped, and reshaped by the most powerful forces in the universe. We thought space was just the stage where physics happened. We were completely wrong. What Einstein revealed in 1915 changed everything we thought we knew about the nature of reality itself. Space and time aren't separate entities floating in some cosmic background. They are woven together into a single fabric that can stretch like rubber, compress like a spring, and ripple like the surface of a pond when cosmic titans collide billions of light years away. These aren't abstract mathematical concepts. They're measurable, observable phenomena that affect every atom in your body right at this moment. Consider this staggering fact when the Laser Interferometer Gravitational Wave Observatory detected two black holes colliding 1.3 billion years ago. But here's what makes this truly mind-bending. You are not just observing this phenomenon from some detached perspective. You're part of it. Your body, this room, this planet, everything exists within this flexible space-time fabric. When massive objects move through space, they don't just travel through it, they reshape it. And that reshaping propagates outward at the speed of light, carrying information about the most extreme events in cosmic history directly to your location. You are literally being touched by the aftershocks of cosmic catastrophes that happened when the universe was a fraction of its current age. The implications stretch far beyond academic physics. This understanding of spacetime's malleable nature is already revolutionizing how we navigate GPS satellites, predict the behavior of massive stars, and search for the most elusive phenomena in the cosmos. Mission planners at NASA now routinely calculate how spacetime curvature will affect spacecraft trajectories. Engineers designing the most precise clocks ever built must account for how Earth's gravity stretches time itself. And physicists like Kip Thorne and Andrea Ghez have used these principles to peer directly into the hearts of black holes and watch matter disappear beyond the event horizon. Tonight, we are going to explore three profound revelations that will forever change how you understand your place in the cosmic fabric. First, we'll discover that what you call gravity is actually a force pulling objects together. It's the geometry of spacetime itself guiding everything along the shortest possible paths through curved reality. Second, we'll uncover how the most extreme objects in the universe don't just bend spacetime, they create regions where space stretches toward infinity and time itself can slow to a crawl. And third, we'll reveal how recent breakthroughs have given us the ability to listen directly to the symphony of spacetime itself, detecting cosmic collisions by measuring how they stretch and compress the very foundation of existence. What you're about to learn isn't just another physics lesson, it's a fundamental reimagining of reality. By the end of this journey, you'll understand that you are not sitting in empty space watching distant objects move according to mysterious forces. You're embedded in a dynamic, responsive medium that connects you to every star, galaxy, and cosmic event across the entire observable universe. The fabric of spacetime isn't just some abstract concept, it's the cosmic web that binds all existence together. If you're ready to discover how the universe literally reshapes itself around you, subscribe and hit the thumbs up button. And here's something to think about as we begin. Spacetime can stretch and compress. What does that mean for the nature of distance itself? Comment below with your wildest theory about what space really is. I'll pin the most mind-bending answer. This understanding represents one of the greatest intellectual achievements in human history, connecting the smallest scales of quantum mechanics to the largest structures in the cosmos. We're about to explore how Albert Einstein's geometric revolution revealed that reality itself is far stranger, more flexible, and more interconnected than anyone had dared to imagine. From the precise ticking of atomic clocks to the collision of black holes billions of times more massive than our Sun, every phenomenon we'll examine emerges from one central truth: spacetime is not passive, it is an active participant in every cosmic dance. Now let's begin our journey into the flexible foundations of reality itself, where space stretches, time dilates, and the very geometry of existence reveals the deepest secrets of how our universe really works. Chapter 1: Fabric revealed what if everything you think you know about space is fundamentally wrong. For thousands of years, humanity imagined space as an empty container, a cosmic stage where objects moved according to invisible forces. Then Einstein came along and shattered this intuition with one of the most profound insights in scientific history. Space isn't empty at all. It's a fabric, and that fabric can be stretched, compressed, twisted, and warped by the presence of matter and energy. Picture the most important thought experiment in modern physics. Imagine you're falling freely in an elevator whose cable has just snapped. In those terrifying moments before impact, something remarkable happens. You feel weightless. Ejects float around you as if gravity has been turned off. Einstein realized this wasn't just a curiosity, it was a profound clue about the true nature of gravity itself. He called it the equivalence principle. And it revealed that gravity and acceleration are indistinguishable experiences. But here's where Einstein's genius truly shines. He took this simple observation and extrapolated it to its logical conclusion. If gravity feels identical to acceleration, then gravity might not be a force at all. Instead, what we experience as gravitational attraction might actually be the result of moving along the straightest possible paths through curved spacetime. When you drop a ball, it doesn't fall because Earth exerts some mysterious pulling force. It follows the natural geometry of warped spacetime around our planet. To understand this revolutionary concept, consider how we normally think about straight lines and a flat surface. The shortest distance between two points is obviously a straight line, but what happens when that surface becomes curved? On the surface of Earth, airlines don't fly in what appears to be straight lines on flat maps. They follow great circle routes that curve across the globe because those represent the shortest distances through curved space. Similarly, objects in gravitational fields follow geodesics, the straightest possible paths through curved spacetime. The mathematical foundation for this insight came from Bernhard Riemann's work on non-Euclidean geometry decades before Einstein. Riemann had developed the mathematical tools to describe spaces where parallel lines could converge, where the angles of triangles could sum to more or less than 180 degrees, and where the familiar rules of flat geometry broke down completely. Einstein realized that these abstract mathematical concepts might actually describe the true geometry of our physical universe. When Einstein published his field equations in 1915, he provided humanity with a precise mathematical description of how matter and energy curve spacetime. The equations reveal an elegant reciprocal relationship. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. This isn't just poetic language, it has a quantitative description of how the fabric of reality responds to the presence of mass and energy. Consider the profound implications of this geometric perspective. Every massive object in the universe creates what we can think of as a depression or curvature in the spacetime fabric. The more massive the object, the deeper the depression. When smaller objects move through this curved region, they naturally follow the contours of the geometry, which we observe as gravitational attraction. Earth orbits the Sun not because of some mysterious action at a distance force, but because our planet follows a geodesic path through the curved spacetime created by the Sun's enormous mass. This geometric understanding explains phenomena that Newton's gravity couldn't fully account for, the slight precession of Mercury's orbit, which had puzzled astronomers for decades, emerged naturally from Einstein's equations as a consequence of how the Sun's mass curves spacetime near Mercury's elliptical path. When British astronomer Arthur Eddington measured the deflection of starlight during the 1919 solar eclipse, he confirmed that light itself follows geodesics through curved spacetime, providing dramatic proof that Einstein's geometric revolution was more than just mathematical abstraction. But perhaps the most mind-bending aspect of this fabric metaphor is how it reveals the dynamic nature of spacetime itself. The fabric isn't rigid, it's responsive. When massive objects accelerate, they create ripples in spacetime that propagate outward at the speed of light. These gravitational waves carry energy and information across cosmic distances, literally stretching and compressing space as they pass through. Modern physics has revealed that This spacetime fabric operates on scales ranging from the quantum realm to cosmic horizons. At the smallest scales, quantum fluctuations constantly create tiny variations in spacetime geometry. At the largest scales, the expansion of the universe itself represents a stretching of the cosmic fabric, carrying distant galaxies away from us, not through space, but with space itself. This understanding transforms how we think about every interaction in the universe. When you walk across a room, you are not moving through empty space, you are following geodesics through the curved spacetime created by Earth's mass. When photons travel from distant stars to your eyes, they follow the natural geometry of the cosmic fabric, carrying information about how spacetime has been shaped by every massive object along their journey. The fabric metaphor also reveals why Einstein's insights were so revolutionary. Previous physics treated space and time as fixed background stages where events occurred. Einstein showed that space and time are dynamic participants in every cosmic process. They can be stretched, compressed, twisted, and deformed. This realization didn't just add new equations to physics, it fundamentally redefined what we mean by reality itself. What we've discovered in this chapter represents just the beginning of our exploration into spacetime's malleable nature. We've learned that space isn't empty and time is an absolute. They form a unified fabric that responds to matter and energy. But this raises an even more profound question. If the fabric of spacetime can be shaped and reshaped, what happens in the most extreme gravitational environments in the universe, where this fabric is stretched to its absolute limits? Chapter 2. Einstein's Revolution. In the summer of 1905, a young patent clerk in Bern, Switzerland, was struggling with a problem that would reshape humanity's understanding of reality. Albert Einstein couldn't reconcile the behavior of light with the prevailing notions of absolute space and time. What emerged from his intellectual struggle wasn't just another scientific theory, it was a complete reconstruction of the foundations of physics that revealed space and time as far stranger and more interconnected than anyone had imagined. Einstein's revolutionary insight began with a simple but profound observation about the speed of light. And like every other phenomenon in physics, light always travels at the same speed regardless of how fast you are moving toward or away from its source. This violated every intuition about motion developed since Galileo. When you throw a ball from a moving train, its speed relative to the ground equals the ball's speed plus the train's speed. But light refuses to follow this common-sense addition of velocities. It always moves at precisely 299,792,458 meters per second in vacuum, no matter what. This cosmic speed limit forced Einstein to abandon the idea of absolute simultaneity. Events that appear simultaneous to one observer occur at different times for another observer moving at high speed relative to the first. Time itself becomes relative, flowing differently for different observers depending on their motion through space. This wasn't just a mathematical quirk, it was a fundamental property of reality that would be confirmed by countless experiments over the following century. But Einstein's 1905 special theory of relativity was only the beginning. While it revealed the intimate connection between space and time, it still treated spacetime as a fixed background arena. It took another decade of intense mathematical work before Einstein achieved his greatest triumph, the general theory of relativity, which revealed that spacetime itself could be curved, stretched, and deformed by the presence of matter and energy. The key insight came from Einstein's realization that gravity wasn't like other forces. When you accelerate in a car, you feel pushed back into your seat. When you experience gravity, you feel pulled downward. But Einstein noticed something remarkable. Both sensations are indistinguishable if you can't see what is causing them. Someone blindfolded in an accelerating elevator couldn't tell whether they were being pushed by acceleration or pulled by gravity. This equivalence principle became the foundation for understanding gravity as geometry rather than force. Working with mathematicians like Marcel Grossmann, Einstein learned the complex mathematics of curved spaces developed by Riemann and others. These abstract geometric concepts provided exactly the tools needed to describe how massive objects could curve the fabric of spacetime itself. What had seemed like purely theoretical mathematics suddenly became the language for describing physical reality. Einstein's field equations, published in 1915, revealed spacetime as a dynamic medium that responds to the presence of matter and energy. The equations showed that massive objects don't just move through spacetime, they reshape it. Imagine placing a bowling ball on a stretched rubber sheet. The ball creates a depression, and marbles rolled nearby follow curved paths around this depression. Similarly, massive objects create curvatures in spacetime, and other objects follow geodesic paths through this curved geometry. The immediate predictions of this geometric theory were stunning. Einstein calculated that Mercury's orbit should precess slightly more than Newton's gravity predicted. And the observation matched his calculations perfectly. He predicted that light should bend when passing massive objects, and Eddington's 1919 eclipse expedition confirmed this prediction, making Einstein an international celebrity overnight. Most remarkably, the equations predicted that space itself could expand or contract, a possibility so strange that even Einstein initially rejected it by adding his infamous cosmological constant. But perhaps the most profound implication of Einstein's revolution was the revelation that spacetime has tangible physical properties. It can store energy, carry information, and even exhibit phenomena like resonance and damping. When massive objects accelerate, they create ripples in spacetime that propagate outward as gravitational waves. These waves stretch and compress space itself as they pass through, carrying energy away from their sources and gradually damping the motion that created them. Einstein himself was skeptical about whether gravitational waves could ever be detected. The effects are extraordinarily subtle. Typical gravitational waves change lengths by amounts billions of times smaller than atomic nuclei. Yet he had unwittingly predicted one of the most remarkable experimental achievements of the 21st century, the direct detection of spacetime vibrations created by colliding black holes. Billions of years ago, the geometric revolution also transformed our understanding of time's relationship to gravity. Einstein's equations revealed that time flows more slowly and stronger. Gravitational fields, an effect called gravitational time dilation. This isn't just theoretical speculation. GPS satellites must continuously correct for the fact that their clocks run faster in the weaker gravitational field high above Earth's surface. Without these relativistic corrections, GPS would accumulate errors of several miles per day. Einstein's work revealed that what we experience as the flow of time is intimately connected to the curvature of spacetime around us. In regions of intense gravity, time slows to a crawl relative to distant observers. Near the event horizon of a black hole, this effect becomes so extreme that time appears to stop completely from an outside perspective. Yet someone falling through that horizon would experience time flowing normally, even as they crossed into a region where spacetime itself becomes infinitely curved. Revolutionary nature of Einstein's insights extends beyond their immediate physical implications. By revealing space and time as dynamic, interconnected aspects of a unified fabric, he fundamentally changed how we think about causality, locality, and the nature of physical law itself. Information cannot travel faster than light, not because of some arbitrary cosmic speed limit, but because the geometric structure of spacetime itself defines what we mean by causation and temporal sequence. Modern physics continues to build upon Einstein's geometric foundation. Quantum field theory describes particle interactions as excitations in fields that exist throughout spacetime. Cosmology uses Einstein's equations to model the evolution of the entire universe from its earliest moments to its ultimate fate. Even speculative theories like string theory and loop quantum gravity attempt to understand what happens to spacetime's geometry at the quantum scale, where Einstein's smooth fabric might resolve into discrete, granular structures. What Einstein achieved between 1905 and 1915 represents one of the greatest intellectual accomplishments in human history. He didn't just solve a few puzzling observations about light and gravity, he revealed that reality itself operates according to principles far more profound and interconnected than anyone had imagined. Space and time emerged not as separate backgrounds for physical events, but as active participants in a cosmic dance where geometry and physics become inseparable. This geometric understanding of spacetime sets the stage for exploring even more extreme phenomena. If massive objects can curve spacetime around them, what happens when we encounter the most extreme gravitational environments in the universe regions? where spacetime is stretched, compressed, and warped beyond anything we can experience on Earth. Chapter 3: Gravitational Waves. On September 14, 2015, at 5:51 a.m. Eastern Daylight Time, humanity heard the universe speak in a language we had never detected before, to black holes, each roughly 30 times more massive than our Sun, completed a final death spiral that had been continuing for millions of years. In the last fraction of a second before merger, they accelerated to nearly half the speed of light, releasing more energy in gravitational waves than all the stars in the observable universe immediately. The space-time distortion was so violent that it briefly made the black holes the most powerful source of gravitational radiation in the cosmos. That cosmic collision happened 1.3 billion years ago, when Earth was populated only by simple single-celled organisms. Yet the gravitational waves it produced traveled across the cosmos at the speed of light, carrying information about one of the most extreme events possible in our universe. When those ripples finally reached Earth, they passed through our planet like a whisper from the deep history of space and time itself, stretching and compressing the fabric of reality. By distances smaller than 1/10th the width of a proton, the detection itself represents one of the most remarkable experimental achievements in the history of science. The Laser Interferometer Gravitational Wave Observatory, or LIGO, consists of two identical detectors, one in Louisiana and one in Washington state, each featuring two perpendicular arms stretching for kilometers in length. Laser beams travel back and forth along these arms, and scientists measure tiny changes in the time it takes light to complete these journeys. When a gravitational wave passes through, it stretches space in one direction while simultaneously compressing it in the perpendicular direction, creating a characteristic pattern that reveals the cosmic event that produced it. To appreciate the extraordinary sensitivity required for this detection, consider the scale of what LIGO measures. But what exactly are gravitational waves, and how do they reveal the malleable nature of spacetime itself? Einstein's field equations predict that when massive objects accelerate asymmetrically, they create ripples in the fabric of spacetime that propagate outward at the speed of light. These aren't waves traveling through space, they are waves of space itself, alternately stretching and compressing the distances between objects as they pass through. Imagine two black holes orbiting each other in an ever-tightening spiral. As they accelerate around their common center of mass, they create a complex pattern of spacetime curvature that changes rapidly with time. This changing curvature radiates outward as gravitational waves, carrying energy away from the system and causing the orbital decay that eventually leads to merger. The waves themselves encode information about the masses, spins, and orbital dynamics of their sources with extraordinary precision. The mathematical description of gravitational waves reveals their unique properties compared to other types of waves. While electromagnetic waves like light can travel through empty space as oscillations in electric and magnetic fields, gravitational waves are oscillations in the geometric structure of spacetime itself. They have no medium, they are the medium. When a gravitational wave passes through a region, it temporarily changes what we mean by distance and geometry in that region. LIGO's success has opened an entirely new window for studying the universe. Since September 2015, the global network of gravitational wave detectors has observed dozens of black hole mergers, each providing unprecedented insights into the behavior of matter and spacetime under the most extreme conditions possible. The observed signals match Einstein's predictions with stunning precision, confirming that massive objects really do curve spacetime, and that this curvature can propagate across cosmic distances as dynamic distortions in the fabric of reality. Perhaps even more remarkably, LIGO and its international partners detected the merger of two neutron stars in August 2017. This event, designated GW170817, provided the first opportunity to study a gravitational wave source using both spacetime distortion detectors and traditional telescopes. The collision was so violent that it created heavy elements like gold and platinum through rapid neutron capture processes, scattering these materials throughout the surrounding region. The gravitational waves arrived at Earth just 1.7 seconds before the gamma ray burst, confirming that gravity and light travel at essentially identical speeds across cosmic distances. The The detection of gravitational waves has profound implications for our understanding of spacetime's properties. These cosmic ripples demonstrate that spacetime isn't just a mathematical abstraction, it has physical reality that can store, transport, and dissipate energy. When black holes merge, roughly 3 solar masses worth of energy gets converted into gravitational radiation and carried away as distortions in spacetime geometry. This represents the most efficient energy conversion process known in the universe, far exceeding the efficiency of nuclear fusion or matter-to-matter annihilation. Future gravitational wave astronomy promises even more dramatic discoveries. The European Space Agency's LIGO mission, planned for launch in the 2030s, will use 3 spacecraft separated by millions of kilometers to detect gravitational waves from massive black holes at the centers of distant galaxies. Ground-based detectors are being upgraded to achieve even greater sensitivity, potentially observing thousands of black hole and neutron star mergers each year. These observations are already revealing surprising properties of black hole populations throughout cosmic history. The masses and spins of merging black holes don't always match theoretical predictions, suggesting that our understanding of stellar evolution and black hole formation needs refinement. Some detected mergers involve black holes with masses that fall in unexpected ranges, challenging models of how massive stars end their lives. Gravitational waves also provide a new probe of fundamental physics itself. Einstein's theory predicts specific relationships between the frequencies, amplitudes, and polarization patterns of gravitational radiation by measuring these properties with ever-increasing precision. Scientists can test whether gravity really behaves according to general relativity in the most extreme environments, or whether departures from Einstein's theory become apparent when spacetime is pushed to its limits. The philosophical implications of gravitational wave detection extend far beyond astrophysics. For the first time in human history, we can directly sense the dynamic nature of spacetime itself. We ray not just observing distant objects through the electromagnetic radiation they emit, we ray feeling the actual stretching and compression of the cosmic fabric as information about extreme events propagates across the universe. This connects us to cosmic phenomena in a fundamentally more intimate way than ever before possible. What gravitational waves reveal about spacetime's malleable nature sets the stage for exploring even more exotic possibilities. If spacetime can ripple and oscillate like the surface of a pond, what happens in regions where this fabric becomes so severely distorted that the usual rules of physics break down completely? How do black holes stretch spacetime to its ultimate limits? Chapter 4: Warp Geometry. Deep in the heart of our galaxy, something impossible lurks in the darkness, a region where spacetime itself has been twisted into such extreme curvature that the normal rules of physics cease to apply. Sagittarius Asterisk, the supermassive black hole at the Milky Way's center, contains the mass of 4.1 million suns compressed into a region smaller than Mercury's orbit around our Sun. The spacetime distortion it creates is so severe that light itself cannot escape from within a critical radius, creating what we call an event horizon, a one-way membrane in the fabric of reality itself. To understand how black holes demonstrate the extreme malleability of spacetime, we need to journey through the increasingly warped geometry surrounding these cosmic monsters. Far from a black hole, spacetime appears nearly flat, and objects follow familiar orbital mechanics similar to planets around stars. But as we approach closer, the curvature becomes more pronounced. Light beams that would travel in perfectly straight lines through empty space begin to bend along increasingly curved geodesics. At 3 times the Schwarzschild radius, the distance that defines the event horizon, something remarkable happens to the nature of orbits themselves. This region, called the photon sphere, represents the closest stable circular orbit that light can maintain around a black hole. Photons following these paths circle the black hole indefinitely, creating a spherical shell of trapped light. Any photon that ventures closer inevitably spirals inward, while those farther out can escape to infinity. This invisible boundary reveals how severely curved spacetime affects even massless particles. The mathematical description of spacetime around a black hole, first worked out by Carl Schwarzschild just months after Einstein published his field equations, reveals the true strangeness of warp geometry. As we approach the event horizon, several bizarre effects become apparent. Time dilation becomes so extreme that clocks appear to run slower and slower relative to distant observers. From the perspective of someone watching from far away, objects falling into a black hole appear to slow down and freeze at the event horizon, their light becoming redder and dimmer until it fades below detection. Yet from the perspective of someone crossing the event horizon, time flows normally. The falling observer sees their own clock ticking at regular intervals, experiences normal passage of time, and detects nothing special about crossing this geometric boundary. This paradox reveals that the concept of simultaneity breaks down completely in severely curved spacetime. Events that are now for one observer occur at completely different times for another observer in a different gravitational environment. Perhaps even more mind-bending is what happens to space itself near the event horizon. The Schwarzschild metric reveals that radial distances become stretched while circumferential distances remain finite. If you could somehow hover just outside the event horizon and measure the circumference of a circle centered on the black hole, you'd get exactly 2 times the radius. But if you tried to measure the radial distance from that circle to the black hole's center, you'd find it requires an infinite coordinate distance to reach the singularity. Space itself becomes infinitely stretched in the radial direction. This geometric distortion creates phenomena that seem to violate our intuitive understanding of space and time. Near a black hole, the distinction between space and time coordinates becomes blurred. What we normally think of as space directions can become time-like inside the event horizon, while temporal coordinates take on spatial characteristics. This isn't just mathematical abstraction, it represents a fundamental transformation in the causal structure of spacetime itself. Modern observations of matter falling into black holes have confirmed many of these geometric predictions. The Event Horizon Telescope's historic image of the supermassive black hole in galaxy M87 revealed the characteristic shadow created by the event horizon's effect on light paths, matter. Spiraling into the black hole creates an accretion disk that glows brilliantly from friction and magnetic field interactions. The observed structure of these disks matches theoretical predictions based on how curved spacetime affects the motion of plasma in extreme gravitational fields. Even more dramatic are the observations of individual stars orbiting close to Sagittarius asterisk. Astronomers have tracked these stellar motions for decades, watching stars follow highly elliptical orbits that carry them within just a few hundred times the event horizon radius. During closest approach, these stars reach speeds exceeding 5,000 kilometers per second, nearly 2% the speed of light. The observed orbital mechanics precisely match Einstein's predictions for motion through severely curved spacetime, providing some of the strongest confirmations of general relativity in extreme gravitational environments. But the geometry near black holes reveals even stranger possibilities than extreme time dilation and spatial distortion. Rotating black holes, described by the Kerr metric, drag spacetime around with them in a phenomenon called frame dragging, or the lens-stirring effect. Near a spinning black hole, it becomes impossible to remain stationary relative to distant observers. The rotation of the black hole itself drags everything, including light, along with it. This creates a region called the ergosphere, where the distinction between space and time becomes even more profoundly altered. The ultimate expression of spacetime's malleability appears at the black hole's center, where Einstein's equations predict a gravitational singularity, a point where spacetime curvature becomes infinite, and the known laws of physics break down at this singularity. The fabric of spacetime itself is stretched to its breaking point, creating a region where our current understanding of reality simply fails. Whether physical singularities actually exist, or whether quantum effects prevent infinite curvature from forming, remains one of the greatest unsolved problems in theoretical physics. Recent theoretical work suggests that black hole interiors might be even stranger than previously imagined. Some models propose that the singularity might be replaced by a firewall of a region of extremely high energy that incinerates anything crossing the event horizon. Other theories suggest that black hole interiors might connect to distant regions of spacetime through Einstein-Rosen bridges or wormholes, though these remain highly speculative possibilities. The study of black hole geometry has also revealed profound connections between gravity, thermodynamics, and quantum mechanics. Stephen Hawking's discovery that black holes emit thermal radiation due to quantum effects near the event horizon suggests that these objects have temperatures and entropies proportional to their surface areas. This connection between geometric properties and thermodynamic quantities hints at deeper relationships between spacetime structure and quantum information theory. What black holes teach us about spacetime's malleability extends far beyond these exotic objects themselves. They demonstrate that the fabric of reality can be stretched, compressed, and twisted to degrees that completely transform our understanding of space-time and causality. Near black holes, the smooth Euclidean geometry we experience in everyday life gives way to bizarre curved manifolds where the shortest distance between two points might involve traveling backward in time, where space can become infinite, and where the very concepts of inside and outside lose their conventional meanings. This exploration of warped geometry around black holes raises even more fundamental questions about the nature of spacetime itself. If the cosmic fabric can be distorted to such extremes, what does this tell us about its underlying structure? How do these geometric distortions affect the behavior of matter and energy in ways we can observe and measure? Chapter 5: Cosmic Stretching. Right now, as you read these words, the universe itself is stretching. Not expanding into some pre-existing void, but literally creating new space between every pair of distant galaxies. This cosmic expansion represents the most dramatic example of spacetime's malleable nature, revealing that the fabric of reality can be stretched on scales so vast they dwarf even the extreme distortions around black holes. What we're witnessing is the continuing aftermath of the universe's violent birth, an ongoing transformation that affects the fundamental structure of cosmic space itself. The discovery of cosmic expansion ranks among the most profound revelations in the history of science. In the 1920s, astronomer Edwin Hubble analyzed light from distant galaxies and noticed something extraordinary. The farther away a galaxy appeared to be, the faster it was moving away from Earth. This wasn't because galaxies were flying through space away from some central location, it was because space itself was expanding, carrying the galaxies along with it like raisins in rising bread dough. To understand how cosmic expansion stretches spacetime, imagine painting dots on a balloon and then inflating it. As the balloon expands, the dots don't move across the balloon's surface, but the distance between them increases as more balloon material appears in the spaces between. Similarly, cosmic expansion doesn't move galaxies through space, it creates new space between them, causing their separation to increase even though they remain relatively stationary within their local regions of spacetime. This expansion affects light traveling across cosmic distances in measurable ways. As photons journey from distant galaxies to our telescopes, the expanding space literally stretches their wavelengths, shifting them toward longer, redder frequencies. This cosmological redshift provides astronomers with a direct measurement of how much the universe has expanded since the light began its journey. Light from the most distant observable galaxies shows redshifts indicating that the universe has expanded by a factor of more than 13 since those photons were emitted. The mathematical description of cosmic expansion emerges naturally from Einstein's field equations when applied to the universe as a whole. Alexander Friedman's solutions revealed that a homogeneous universe filled with matter and energy cannot remain static, it must either expand or contract. Einstein initially resisted this implication, adding his cosmological constant to allow for a static universe, but later called this the biggest blunder of my life when Hubble's observations confirmed cosmic expansion. What drives this cosmic stretching reveals fundamental properties of spacetime itself. In the earliest moments after the Big Bang, the universe underwent a period of exponential expansion called cosmic inflation, during which spacetime stretched faster than the speed of light. This wasn't a violation of relativity, nothing was moving through space faster than light. Instead, space itself was expanding so rapidly that regions originally in close contact became causally disconnected, their separation growing faster than light could travel between them. Modern observations have revealed an even more startling aspect of cosmic expansion: it's accelerating. Supernovae in distant galaxies appear dimmer than expected based on their redshifts, indicating that the expansion rate has been increasing over the past several billion years. This acceleration requires a form of energy that acts oppositely to gravity, stretching spacetime rather than compressing it. We call this mysterious component dark energy, and it appears to comprise roughly 68% of the total energy density of the universe. The nature of dark energy represents one of the greatest puzzles in modern cosmology. Leading candidates include a cosmological constant of fixed energy density inherent in empty space itself, or more exotic possibilities like dynamical scalar fields that evolve over cosmic time. Some theories propose that dark energy might not be energy at all, but rather a modification of Einstein's field equations that becomes apparent only on cosmic scales. To appreciate the scale at which cosmic expansion operates, consider the observable universe's size. Light from the cosmic microwave background radiation released when the universe first became transparent roughly 380,000 years after the Big Bang has been traveling for nearly 13.8 billion years to reach us. During this journey, cosmic expansion has stretched the universe by such an enormous factor that the region that emitted this radiation is now roughly 46 billion light-years away from Earth. This cosmic stretching affects our understanding of distance itself on the largest scales. When astronomers discuss distances to very remote objects, they must specify what they mean. The light travel time distance tells us how long the light has been traveling. The co-moving distance accounts for cosmic expansion and represents how far away the object is now. The angular diameter distance determines how large the object appears in our sky. These different distance measures diverge dramatically for very distant objects due to the expansion of spacetime. Cosmic expansion also provides a natural explanation for one of the oldest puzzles in astronomy, Olber's paradox. If the universe were infinite, eternal, and filled uniformly with stars, the night sky should be blazing with starlight in every direction. The resolution involves cosmic expansion and the finite age of the universe. Most of the universe remains beyond our observable horizon, and even visible light from distant sources gets redshifted into infrared wavelengths by cosmic expansion. The study of cosmic expansion has revealed that spacetime possesses remarkable structural properties. The universe appears to be remarkably flat on large scales. Its geometric curvature is extremely close to zero. This flatness requires an extraordinary fine-tuning of the universe's initial energy density. Small deviations from critical density in the early universe would lead either to rapid collapse or to expansion so fast that matter could never clump together to form galaxies and stars. Current measurements indicate that the universe's expansion is described by a handful of fundamental parameters that determine cosmic geometry and evolution. The Hubble constant describes the current expansion rate. The density parameters specify the relative contributions of ordinary matter, dark matter, and dark energy. The equation of state parameter characterizes how dark energy's pressure relates to its density. These parameters, measured with ever-increasing precision by space-based telescopes and surveys of millions of galaxies, define the cosmic spacetime metric on the largest possible scales. Future observations promise to reveal whether cosmic expansion will continue forever or eventually reverse if dark energy maintains constant density as space expands. The acceleration will continue indefinitely, leading to a cold, empty universe where even atoms eventually decay. Alternative models predict that dark energy might evolve, potentially leading to scenarios where expansion slows, stops, or even reverses into cosmic contraction. The philosophical implications of cosmic expansion extend beyond astrophysics. The stretching of spacetime on cosmic scales reveals that the universe itself has a history of beginning, and evolution, and potentially an end. This connects the largest scales of physics to fundamental questions about time, causality, and existence itself. We exist during a brief epoch when cosmic expansion has created conditions suitable for complex structures like galaxies, stars, and planets to form and evolve. What cosmic expansion reveals about spacetime's malleability prepares us to explore an even more fundamental question: how do we actually measure these subtle stretches and compressions of the cosmic fabric? The techniques that allow us to detect gravitational waves, map cosmic expansion, and probe the geometry around black holes require extraordinary precision and ingenious experimental approaches.